And welcome back, students, as we get into our next lesson. And today we're going to discuss thinking recursively. Specifically, we're going to look at some recursive design techniques and also that of binary search. So getting started with today's lesson, when you're defining and using recursive methods, you do not want to be continually aware of the stack and suspended computations. That's not something you as a programmer should have to worry about. The power of recursion comes from the fact that you can ignore that detail and just let the computer do the bookkeeping for you. At the end of the day, the computer does work. You have a nice, easy, relaxing time because you trust the computer to do it as long as you don't encounter recursion. So a good example of this, of course, was our power method that we had written back in the recursion demo 2. So back in that lesson, the way to think of the definition of power was that power is x to comma n, which returns the power x comma n 1 times x. And that was because x to the n is always equal to x to the n minus 1 times x, which is the correct value to return, provided that the computation will always reach a stopping case and will correctly compute the stopping case. So those are little caveats that we have with that. Now, when we look at methods that return a value, all right, the key criteria for that is, after we've checking that the recursive part of our definition is correct, all we need to check is that the chain of recursive calls will always reach a stopping case and that the stopping case will always return the correct value. So in other words, all you need to do to check is the following 3 properties are satisfied. First, that there's no infinite recursion. A recursive call, of course, can lead to another recursive call, which will lead to another, so forth. But every such chain of recursive calls eventually should reach a stopping case. If it doesn't, you're going to have problems. You're going to run out of memory, etc. So you want to make sure that there's no infinite recursion in your algorithm. Also, you want to make sure that each stopping case returns the correct value for the case. Using the stopping case, you should be able to expect or have some idea of what those outputs might look like. So a stopping case should work, and it shouldn't just like puke out garbage. It should puke out what you're expecting to be an answer. Like, so for example, we look at our power example. Anything to the power of 0 we know is going to be 1, so that's our one of our stopping cases there. So it makes it pretty easy to plug a 0 in for a stopping case in that instance because we know what the correct value should be. And then for the cases that involve recursion, if all recursive calls return the correct value, then the final value returned by the method is the correct value. Now, if we look at this same criteria with void methods, we can apply the exact same rules. So if we show that our recursive void method definition satisfies the following criteria, you'll know that your void method performs correctly. And you'll notice that they're exact same rules. There's no infinite recursion. Your stopping case is performing the correct action. And for the cases that involve recursion, if all your recursive calls perform the actions correctly, then the entire case is going to perform correctly. All right. So now that we kind of review those 3 rules, let's get into talking about binary search. So this is another recursive method that we're going to develop that's going to search an array to find out whether or not it has a specified value. So for example, the array may contain a list of numbers that for like a store reward cards that are no longer valid. A store clerk needs to search the list to see if a customer's card is valid or invalid. So the indices of the array are the integers 0 through final index. So to make the task of searching the array easier, we're going to assume for this first purpose that the array is sorted. Now if your array was not sorted, obviously all you need to do is go through and do a sort. So once it's sorted, we know the following, that a of 0 is less than or equal to a of 1, which is less than or equal to 2, less than or equal to ... all the way up to a of your final index. In fact, our binary search algorithm that we're going to use in this example is going to require that our array is already sorted. So again, if you have an array that's not sorted, what you're going to need to do first, you're going to want to sort the data in that array. In fact, that's the easiest way to analyze data, like when you start looking at big databases and stuff like that, is that the data is in some kind of sorted pattern when you do your analysis. It doesn't have to be stored in a sorted manner, but when you go to use it, it's good to sort it so that way you can analyze it easier. All right, now when we're searching the array, we're likely going to want to know both whether the value is in the array, and if it is in the array, where is it? So for example, let's say we're searching for a reward card number, then the array index may serve then as a record number. Another array index by the same indices may hold things like phone number or other information used for reporting a suspicious card. So hence the sought after value is in the array, and we're going to have our method return an index of where the sought after value is located. If the value is not in the array, our method will return -1. The array may contain repeats, which is why we say an index and not the index, because you could technically have multiple things reoccurring. If there's like, let's say, we're looking at a phone number, for example, was, let's say, in there. If you have, let's say, individual records per patron in the array, and let's say it's a husband and wife, well, they might share a phone, and they may not, but let's just say for instance, they share a phone, or even more likely, they share an address. Well, if, let's say, that address, or the phone number, or whatever we're looking at as that record, is shared, you could have multiple instances of it, but you could have, obviously, different things that they correspond to. All right, so let's proceed to produce an algorithm in order to solve this task that we have just examined. It's going to help us visualize the problem in very concrete terms. So let's think about it this way. Suppose the list of numbers is so long that it takes a book to list them all. Now, if you're the clerk and are handed a reward card, you have to check to see if it's on the list and hence if it's invalid. So how would you proceed about doing that? Well, if you're the clerk, you're probably going to open the book somewhere in the middle, or maybe at the beginning or wherever, but maybe in the middle, and you're going to check to see if the number's there. Well, because remember, it's all smallest to largest, so if it is not in the middle, right? So if it's smaller than it, well, we're going to go backward in the book. If it's larger than the middle, well, we're going to work towards the end of the book. All right, so let's look at this algorithm now, and this is going to be our first version of it. So we're going to say, well, the mid is equal to the approximate midpoint between 0 and final index. So if our key is equal to the array of where mid is, we're going to return mid. Otherwise, if it's less than it, we're going to search through a of 0 through a of mid minus 1. And if it's greater than it, we're going to search through a of mid plus 1 through a of final index. Now, because the search of the sorted list are small versions of the very same task we're designing the algorithm to perform, this algorithm naturally lends itself to the use of recursion. The smaller list can be searched with recursive calls to the algorithm itself. Now, our pseudocode right now in its current form is a bit too imprecise to be easily translated to Java code. And the problem of that is, not necessarily what we see, but how we handle the recursive call. So there are two recursive calls actually shown within our code that we need to define. We have search a of 0 through a of mid minus 1, and search a of mid plus 1 through a of final index. Those two lines right there are what we need to translate over into some recursive code. So in order to do that, let's look at this with more parameters. All right, we need two more specifically in order to implement these recursive calls. We need a recursive call that specifies that a subbranch of the array is to be searched. In one case, it is the elements indexed by 0 through mid minus 1. In the other, it's the elements indexed by mid plus 1 through final index. The two extra parameters will specify the first and last indices of the search, so we will call them, and naturally, first and last. So let's look at this algorithm now with a refined approach. So instead of using 0 and final index, we can express pseudocode more precisely as follows. So to search a of first through a of last, we're going to do the following. Mid is equal to approximate midpoint, first and last. That hasn't changed. If key equals a of mid, return mid. That hasn't changed. Where we change it now is in our else ifs. So else if key is less than a of mid, return the result of searching a of first through a of mid minus 1. Else if key is greater than a of mid, return the result of searching a of mid plus 1 through a of last. And notice we switch those out, so instead of saying 0 in last index, we now have first and last. All right, so to search the entire array, the algorithm will be executed with the first set equal to 0 and the last set equal to final index. The recursive calls will then use other values for first and last because we're not hard coding them in to saying, hey, look at 0, hey, look at the last. Instead we're saying, hey, look at the first or look at the last. It makes it a little bit more concise for what we need. So for example, the first recursive call would set first equal to 0 and last equal to the calculated value, mid minus 1. That gets us to our stopping cases. So as with any recursive algorithm, we have to ensure that our algorithm is going to end rather than produce infinite recursion, because it's obviously not going to be good for us if we have infinite recursion in our hands. If the sought after number is found on the list and then there is no recursive call and the process terminates, we need still some way to detect whether or not the number is on the list. So on each recursive call, the value of first is increased or the value of last is decreased. Pretty simple and straightforward. Now, the caveat with this is if they ever pass each other and first actually becomes larger than last, well, then we're going to know that there's no more indices left to check, and the number is not in the array. Now, if we add this test to our pseudocode, we're going to kind of obtain a more complete solution. So here's our pseudocode for binary search. All right? So this is an algorithm, search A of first through A of last. And of course, we have our precondition. So to locate the value key, we're going to say if first is greater than last, which is our stopping case, return -1. Else mid is equal to approximate midpoint between first and last. If key equals A of mid, that's one of our stopping cases, we're going to return mid. Else if it is less than A of mid, and this is of course one of the cases of recursion, we're going to return the result. Else if key is greater than A of mid, which is our other case of recursion, we're going to return the result of searching A of mid plus 1 through A of last. Now, obviously it's in pseudocode, and you can kind of see how we could start taking that pseudocode, translating it over to Java. So let's go ahead and do so. That result, of course, is shown in the binary search class in the class materials, which I happen to have right here. So this is what the code would actually look like. So here's our class, binary search, and then we have our method right here called search. Right? And you'll notice that it takes the parameters of an int array, int first, int last, and int key. So in here it says int result is equal to 0, which is just done to keep the compiler happy. We're going to check to see if first is larger than last. If it is, we return -1. Otherwise, we're going to say int mid is equal to first plus last divided by 2. Remember, you do this because this will tell you what is the middle number. You don't have to worry about rounding or anything like that because, again, it's an int. So if key equals A of mid, then result has to equal mid. So it has to be the middle point. Else if key is less than A of mid, result equals search, because that's the name of our method, A, comma first, comma mid -1, key. Right? And of course, that right here is your recursive method, the first one. The other one, of course, you see if it's greater than it, it's the exact same thing, except here we have mid plus 1. Right? Either way, what we're going to do is we're going to run that, and this will generate recursive calls, and at the end, once this is finished, we return result. Now, the method search is an implementation of the recursive algorithm given on our previous page. The diagram of how the method performs the simple array, or on a sample array, is performed or shown, on the next slide. And the binary search demo illustrates how the method search is used. So let's look at the diagram here first. So here's our execution of the method search. So in here we have the key is 63. All right. So you'll notice that here it's the first. Here's last. We have numbers 15 to 90. So the midpoint right here would show up A of 4, right, because it's going to count the indices 0 through 9. Well, half of that would be technically 5. So that'd be A of 4, because remember that array started 0. So it's still going to look right here. This is my halfway point. Right? And it's going to identify that, well, it can't be in this half here. So I'm not even going to look at this set data. I'm going to look at this set data. And I'm going to take this data. I'm going to do the same thing. I'm going to chop it in half. Where's the midpoint? Boom, right here at A of 7. Okay. Then it's going to take that. Now I'm down to these two numbers. I have a first and last. All right. So then we do our midpoint again. And so mid equals 5 plus 6 divided by 2, which is 5. So it's on itself. A of mid is A of 5, which equals 60. So the key was found. And we're going to return 5 because that would be the index in which it was found. All right. So before I look at the demo, let's just take a look at the final version. You'll notice that the method search involves a more general problem than the original task. Our goal is to design a method to search an entire array, yet the method will let us search any interval of the array by specifying the indices first and last. Now, this is something that may commonly occur when designing recursive methods. Frequently, it's necessary to solve a more general problem in order to be able to express the recursive algorithm. In this case, we only want the answer in the case where first and last are set equal to 0 and final index. However, the recursive calls will set them to values other than 0 and final index. All right, and before we talk about checking recursive criteria, let me just go ahead and show you the demo. So in our demo here, you'll notice I have an array set up right here. I have my final index. I'm setting that to 9 because that means that the final value in this array should be 9 because that means there should be 10 values in here. I'm going to say array contains. I'm going to loop through printing out the each of the values of the array, do print line statements, and we have an int called result. Then I'm going to use this loop here, and I'm going to call result is equal to binary search. And of course, here's my parameters that I'm passing: a, which of course is my array, 0, which is the first index, final index, which of course we already know is 9, and key. Then if result is greater than or equal to 0, we're going to say that the key is at index result. Otherwise, we're going to say that it's not in the array. So if I run this code, you can see it printed out all the numbers in the array. All right. If we wanted to make this a little more beautiful, we could have done like a print line, for example. And if we had run that again, you see it prints out each of those values of the array on their own line. Here's our two print line statements. It says -3 is not in the array, -2 is not at the index 0, -1 is not in the array, 0 is at index 1, etc., 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 all the way until we get to the last value here. 4 is at index 3, because it's going to look to see if those are in the array. Okay. So, getting back to checking recursive criteria, because remember when we talked about recursion, we said there's 3 criteria for our recursion to meet. So, is there infinite recursion? No, because in this case we have a stopping case, and it successfully meets the stopping case, and stopping case should execute correctly. And it does. It gets us the results that we expected in this scenario. And for each of the cases that involve recursion, if all the recursive calls are performing the actions correctly, which they are, then the entire case has performed correctly. So because the method search passes all 3 of our tests, it's a good recursive method definition. So keep that in mind as you start looking at your own method definitions for recursion, that you can pass these 3 tests as well. All right, and that's going to conclude it for today, folks. A little bit longer one, but a lot to kind of sink our teeth into. So until next time.